So this video should function as a bit of a introduction to inverse functions. So let's just jump into it. An inverse function is a function that is the exact opposite of some original function. So basically what's going to happen with our inverse functions is all the x and y values are going to be swapped directly. So this is why for an inverse function to exist, the original function must be 1-to-1. And you can hopefully see why that has to be the case. Because I've got here y equals x squared. You can sort of see the whole thing here. If I'm going to swap the x and the y values, which is basically what an inverse function is, then if -2 goes to 4 and +2 both go to 4, then I have a problem because how do I swap them? Because -2 goes to both. So I can't make a direct swap there because this function is many to one. So you can maybe begin to have an intuition for why, for an inverse function to exist, it has to be 1-to-1. So let's run through a few things. The notation for an inverse function is this: f to the power of -1 and then x. And this is important because that is scarily similar to this. So this is not to be confused with the reciprocal function, which is f of x all to the power of -1, which means 1 over f of x, which is a very different function. So when we're doing the inverse function, we put f to the -1 and then we put the x. Okay, you'll hopefully see how it all comes together in a minute. So let's have a look at an example. Let's fully define the inverse of the function f from 0 to infinity, mapped onto all real numbers, f of x equals x squared. Now you'll notice here a restriction on the domain. And that's because, as we said before, f of x equals x squared is not 1-to-1. So we need to actually make it 1-to-1. And the way we're going to do that is going to restrict it to be from 0 to infinity. So if I delete that black line and that point there, you can now see this is actually 1-to-1. This pink line is this function fully defined from 0 to infinity, f of x equals x squared. But we're only considering values from 0 up to infinity. Now, what we want to do now is we want to find the inverse function, and there's a process that we can go through to do that. So the first thing you need to write, if you don't write this on the assessment, you will potentially lose a mark. You need to write the following. You need to let y equal f of x, because this is entirely in function notation, and we're going to introduce a y. So we need to say that y equals f of x. And then what you have to write is swap x and y. Okay? Because that's what we're trying to do. We're trying to swap the coordinates. We're trying to swap all x and y coordinates and see what happens. So what we'll get here is, what we'd had was y equals x squared, essentially this, because f of x equals y. So y equals x squared, swap x and y. So we get x equals y squared, literally just directly swap them. And then what we get is we get y equals the square root of x, just rearranging for y. Now, you got to be very careful. You're probably thinking, okay, I have to do plus or minus the square root of x. But we have to be very careful here. Now it gets a bit more complicated. We're only interested in x values greater than or equal to 0. So we're interested in the inverse function that is from 0 to infinity. So really only interested in the positive portion of the graph, of the inverse function graph. And you'll see what I mean by that in a second. So what we have at the moment is y equals the square root of x. So that's going to be the rule for our inverse function. And as you can see, y equals square root of x is this graph here, is this green line. And look what you notice. 2, 4 became 4, 2. And that's true for every point along here. The x and the y values will make a direct swap. Okay, and then, so you're probably thinking, how do we fully define the inverse function? Well, this is a really, really important point. Because the x and the y values swap, you're making a direct swap between x and y values. The range of your inverse function is equal to the domain of your original function. And similarly, the domain of your inverse function is equal to the range of your original function. And that's because you're making a direct swap. So think about it like this: domain and range swap. Okay? The domain and range to make a direct swap. Now, let's fully define our inverse function, which is this. Okay, in this case, it so happens that the domain and range are exactly the same. So when we make that swap, it looks like we haven't swapped anything, but I have actually made a change here where the domain of this inverse function was the range of the original function. Now, the range of the original function, you can see, starts at 0, goes up to infinity, including 0. So this has made the swap. It just so happens that in this example, the domain and range are the same, but we did swap them. Okay, and what other interesting thing you'll notice are there's some interesting points here. If I put a point at the intersection there, and obviously it's 0, 0, what's quite unique about these points is that they intersect on the line, and I encourage you to think about what line that they intersect on. Because if you swap x and y values, but the x and y values are the same, then they must intersect on this orange dashed line, which hopefully you've guessed by now is the line y equals x. Okay, so a couple of things there. The inverse function, you're swapping the x and y values, they're going to intersect on the line y equals x. And the domain and range make a direct swap. Hopefully that clarifies one of the more simple examples of what an inverse function is.